This update concerns the latest scientific findings surrounding 3I ATLAS, the third verified interstellar object ever observed passing through our solar system, and one that is rapidly becoming the most chemically puzzling visitor astronomers have encountered. Earlier today, NASA circulated a newly processed sequence of high-resolution spectral readings, and the reaction across the scientific community has been immediate, cautious, and intensely focused. Researchers expected these new spectra to simply reinforce earlier assumptions: the presence of carbon-bearing volatiles, radiation-processed dust grains, metallic residues, and the kinds of primitive interstellar compounds typically cataloged in existing reference libraries. Instead, the updated data revealed something no one had realistically anticipated: a set of spectral absorption structures that do not align with any known mineral, ice, metal, or cometary compound recorded in decades of laboratory measurements. NASA maintains vast databases containing spectra of thousands of materials from Earth, rocks, and Martian analog samples to artificial alloys, cometary residues, chondritic meteorites, interstellar dust simulants, irradiated ices, and even experimental high-pressure structures generated in diamond Donville chambers. Yet, in every comparison run, the new feature appearing in the latest 3I ATLAS data failed to find a match. The anomalous signature takes the form of a narrow way, sharply defined absorption line occurring in a wavelength interval, usually dominated by transitions associated with the iron group elements. But instead of resembling iron, nickel, cobalt, manganese, chromium, or any of the alloyed variations that often appear in meteoritic matter, the absorption depth and fine-scale structure of the feature exhibit a pattern that has never been measured in any terrestrial or extraterrestrial sample. NASA reprocessed the data repeatedly to rule out instrument malfunction, detector drift, calibration issues, or cross-contamination from background solar emissions. To strengthen confidence further, 2 independent observatories, one ground-based and one operating outside Earth's atmosphere, captured nearly identical spectra of the same region of the object over a similar time window. This dual confirmation eliminates the possibility of noise, computational artifacts, or instrument interference. In short, the feature is real, reproducible, and intrinsic to the object itself. What is even more remarkable is the way this feature behaves as 3I Atlas moves deeper into its solar passage. Typically, many known materials exhibit weakening or broadening absorption features as they heat up near perihelion, because thermal agitation disrupts molecular structure and affects electronic transitions. But the unusual line in the 3I ATLAS spectra demonstrates the opposite effect, becoming stronger, more defined, and more pronounced as the object is heated by the sun's radiation. Such behavior implies a material phase or electron configuration that responds in a non-standard way to rising temperatures. It may indicate a compound formed under conditions fundamentally different from anything in the early solar system, perhaps from an environment involving extreme pressure, exotic elemental abundance ratios, or prolonged exposure to cosmic radiation fields. Adding another layer of complexity, the spectral line undergoes splitting when exposed to fluctuating solar wind conditions. In laboratory settings, a similar effect is often associated with magnetic field interactions or with materials that possess asymmetric electron orbitals. However, none of the cataloged minerals known to form naturally in planetary systems exhibit this exact kind of magnetic length line division under comparable conditions. The splitting suggests that the compound responsible for this feature has unusual magnetic or electronic properties that do not belong to any substance we have ever recovered from asteroids, comets, or interplanetary dust streams. Taken together, these observations strongly imply that 3I Atlas is carrying matter shaped by chemical pathways or physical environments not available in our solar system. Preliminary modeling provides several potential explanations, though none are confirmed. One possibility is that the object once originated from the interior of a super-Earth-class planet, where pressures far exceed anything inside Earth's mantle. Such pressures could support the formation of exotic crystal phases unknown in our geological record. Another scenario suggests that the object may have formed inside a carbon-rich protoplanetary disk, where unusual abundance ratios could drive chemical evolution toward carbon-dominant, polymer-like, or metallic carbon hybrid structures. Alternatively, the material might represent a kind of radiation-sculpted interstellar crystal, shaped over millions of years in cold, low-density environments far from the energetic conditions of star-forming regions. A more speculative but physically possible explanation is that it belongs to a branch of chemistry rarely accessible in standard laboratory settings, a chemistry based on extreme temperatures, prolonged cosmic irradiation, or trace elemental mixtures that seldom occur in our region of the galaxy. NASA emphasizes that these are only hypotheses. No definitive conclusion has yet emerged. Scientific caution remains high because the data is new, the signature is unprecedented, and the range of possibilities is large. Despite the unusual nature of the observations, NASA stresses that nothing in the spectra suggests any artificial or engineered origin. The detected features behave as natural physical phenomena governed by standard physics and chemistry, just not by any form of chemistry previously observed in our immediate cosmic neighborhood. The most accurate description at this stage is that 3I Atlas contains chemically unfamiliar material unlike anything currently documented in solar system geology or meteoritic analysis. For the scientific community, this alone is monumental. In all previous interstellar object detections, including -1I Oumuamua and 2I Borisov, the materials involved ultimately resembled known carbonaceous compounds, volatile ices, or dust aggregates. 3I ATLAS is the first to exhibit a spectral identity with no match in our established records. The focus now shifts to what researchers can learn as 3I Atlas continues its outbound trajectory, while the heated state spectra near perihelion have revealed a unique set of high-energy signatures. The next phase of observation will involve the acquisition of cool temperature spectra, which often expose features hidden when a surface is dominated by thermal emission. As the object cools, the anomalous line may widen, shift, or reveal companion features that indicate whether the material lies on the surface, is embedded beneath a thin crust, or exists only as a transient ionized shell interacting with solar wind particles. Cooler spectra can also allow scientists to distinguish between crystalline, amorphous, or composite material states, and may expose vibrational or rotational transitions that remained masked earlier. This will help determine whether the compound is a solid mineral, a complex molecular assembly, or a hybrid structure that defies easy classification. In addition to spectral analysis, astronomers are watching closely for dust release or fragmentation events that could provide direct physical samples. Even microscopic grains captured by heliosphere-embedded dust collectors, or by chance Earth-intercepting streams, could allow laboratory examination of this unfamiliar substance. If such particles were recovered, a difficult but not impossible scenario, scientists could measure isotopic ratios, crystal lattice arrangements, thermal decomposition pathways, and magneto-optical properties under controlled conditions. Such data would decisively test the current hypotheses about the object's origin. For now, however, researchers must rely solely on photons collected from across millions of kilometers, and even with this limitation, the information they carry is already reshaping theories about how matter forms and evolves in interstellar space. The weaker secondary features in the near-infrared spectrum provide additional hints. These structures bear a partial resemblance to vibrational transitions seen in certain exotic carbides and in polymer-linked grain networks, but only partially. Their spacing, symmetry, and harmonic progression differ from all known sample categories. This mismatch implies that the molecular chains or lattice bonds within the unidentified 3I Atlas compound may follow a geometry not produced in conventional solar-type environments. Such differences could arise from atypical temperature gradients, unique elemental ratios within the parent star system, or extended exposure to interstellar radiation fields that restructure bonds and push material into metastable states. If confirmed, this would mark the first direct evidence that interstellar chemical evolution can produce complex structures completely absent from our own planetary system. NASA's internal briefing documents describe the detection with cautious precision, using the language of strict scientific discipline, material signature inconsistent with all known analog samples. In practical terms, this means that as of today, researchers cannot classify the object's composition under any existing mineral, molecular, or crystallographic category. That alone elevates 3 IATLAs from a routine scientific curiosity to a high-priority target of astrophysical research. Each new dataset adds to a growing picture of a visitor carrying matter forged in an environment fundamentally unlike our own. The implications extend beyond planetary science into astrophysics, chemistry, and even the study of galactic material transport. If 3I Atlas is carrying a compound formed under exotic conditions, it may represent a piece of a distant planet, disk, or molecular cloud preserved across interstellar distances and delivered to our solar system by pure chance. As the object continues moving away from the Sun, the next major challenge involves modeling how the anomalous feature interacts with decreasing solar flux. If the line weakens in a predictable fashion, researchers may be able to derive the compound's excitation thresholds, magnetic moments, and thermal stability ranges. If the line behaves unpredictably, strengthening, splitting further, or shifting under low-temperature conditions, scientists may need to consider even more unconventional explanations, involving metastable electronic states or multi-phase crystalline structures. Either outcome will significantly refine the theoretical boundaries of interstellar chemistry. For now, the key scientific points remain clear. The anomalous spectral feature does not match any known natural material. Multiple observatories independently confirmed the signal, ruling out instrument error. The signature strengthens as the object heats, which is atypical and implies unusual thermal behavior. Line splitting under solar wind variations points to exotic, magnetic, or electronic characteristics. Several plausible natural origins exist, but none have been validated. This is the first interstellar object to display a fully unique, chemically unfamiliar signature. The unfolding situation surrounding 3I Atlas represents an extraordinary moment in modern astronomy. Every new reading expands our understanding of what interstellar matter can be, and challenges long-standing assumptions about the limits of natural chemistry. With each passing day, as scientists gather more spectra and refine their analyses, the object becomes not just a visitor from another star system, but a messenger carrying physical evidence from a region of the galaxy, where the rules of material formation may differ subtly or dramatically from those we know. The investigation is ongoing, the data stream continues, and the scientific community expects additional features may emerge as the object cools, rotates, and reveals more of its unknown composition. For now, 3I stands as the most scientifically intriguing interstellar object ever detected, a silent traveler, whose chemistry does not exist anywhere in our current geological or meteoritic archives, and whose presence is rewriting the boundaries of what we believe interstellar matter can become.